Ngalakin Khadijan Nyunga Boja.
Okay, good morning everyone. So let's start our so-called first practical class of the ELEC 5505, the power system analysis. We are currently having this class on Thursday. This is totally because of the public holiday on Monday this week. So from next week onward, this practical class will return back to Monday. So in other words, after we finish this session on this Thursday, so in the week 3 next week, we are going to have this session on Monday. Okay, so don't just be fooled by this confusion timetable. And in our first practical class today, we are going to focus on the contents introduced in our first lecture in week 1. And in week 1, in the chapter 1 of this unit, we just review some fundamental knowledge of the power system analysis. So today, in the questions we discussed in the class, you can find that they're pretty simple. And if you have done the foundation unit in your bachelor program, like the ENIC 2002 a long time ago, so you should be able to solve all the questions without any problem. Okay, so this is the contents of this session. And I hope you can just download the question set from LMS. And under the tutorial folder, you should be able to find 2 PDF files. One of them is the tutorial questions with the brief solutions. Okay, so please download it. And the documentation given in that PDF should be the same as the one I shown on the screen. And in this tutorial, we have in total, I think, 10 questions. 9 or 10 questions in total. Within these 45 minutes, I'm definitely not able to finish all the questions. And also, I plan to give you some details when we go through a discussion of questions. So I will be slow. This means we will not be able to finish everything. So after this session, the questions that we can't finish in this practical class will be a homework. Please try them out at home. They must be very helpful for your future study in this unit. Okay? Okay, now let's just start from the question number 1. Okay, all the questions are pretty fundamental, but I just use this question to give you some warm-up, to recall something we learned before. Okay, in the question number 1, so we are requested to convert the following, okay, be careful the keywords, instantaneous currents to phasors, using cosine and omega t as the reference. Please give your answers in both rectangular and polar form. And then we got A, B, and C, the 3 questions. So for this question, again, in the solution, you have already seen how we derived the final answer. But in our works, so we want to use some review of the knowledge points to help you to know how to do these questions. Okay. So the first question, the first part is, what is the instantaneous current? This is so-called instantaneous current, means the current is a function of time t. So normally, we are going to write down this instantaneous current as IT. And in most of cases, in the 3-phase power system, the instantaneous current should be a function of cosine or sine. So for example, in the part A, you can see the IT equals 400 square root of 2 cosine omega t minus 30 degrees. I just copy this in here, right? Cosine omega t minus 30, right? Minus 30 degrees. I know most of you have known this in very well, but just in case you forgot it, okay? So on the right-hand side of this cosine function, there are 3 key factors. The first one, the amplitude. Normally, this 400 by square root of 2 means the maximum current that this AC current can reach. Okay. Next one, omega. Omega is called angular frequency. Omega is actually equal to, if you want to use a regular frequency to represent it, so omega is 2 pi by f. F is the regular frequency in hertz. What is unit for omega, for angular frequency? Okay, that unit should be radians per second. Okay, 2 different things. Finally, this negative 30 degrees is the phase angle for this AC current. So if you want me to just plot or sketch this function in terms of time, we can do that quickly. First of all, the shape of this instantaneous current is a cosine function. So the shape remains same as cosine function. And because in this question, the omega was not given, so I don't know what's the frequency. We just assume that is known, okay? And because the phase angle is negative 30 degrees, so the whole thing will be shifted to the right by 30 degrees. But in the time domain, you will not be able to see what is the degrees because we are using time as the horizontal axis. What is the relationship between the phase offset with the time delay? Okay, that thing is given here. So if you know your phase angle, for example, phi over 2 pi is equal to the delay delta t over the period of this cosine function. Again, because we don't know what is the omega, so we don't know the frequency f. If you do not know the frequency f, you will be not to find the t, but we assume it's known, okay? So 2 pi is known, capital T period is known. Phase angle delay is negative 30 degrees. By using these 3 informations, we should be able to determine the delay, delta t. After that, we know the delta t is given here. So this offset is the delta t. So that means this cosine function will be delayed by this delta t time interval. And then because it's delayed, so we should start plotting our cosine function from this point. Cosine, the shape of cosine looks like this for one whole period. And then because this is a periodical signal, so repeat it again and again, and so on. So now in this graph, in this sketch, we are just showing one single complete period, okay? This time axis, this is our instantaneous current. The amplitude, so 400 by square root of 2, should be the maximum current that this instantaneous current can reach. So we put 400 by square root of 2 at here. At the bottom, of course, you have negative 400 by square root 2. Okay, this is everything we have. And what we are going to do is to convert this time domain instantaneous current IT into, we call that as a frequency domain. Okay, so in other words, that is the phasor form of the current. So when you convert a function from time domain to the frequency domain into the phasor form, what we need to notice? Okay, here, I give you a quick result here. This is in time domain. We have this instantaneous current. After we finish conversion, the phasor form will be in the frequency domain. In the frequency domain, the time will not be an important factor at all because we focus on the frequency stuff. So in other words, after you finish conversion, you will get a new notation, capital I. This capital I is not a function of time t anymore. And on the right-hand side of this phasor current I, normally we copy down the amplitude as the magnitude of this I, phasor. Phasor is vector, I'll show you later, okay? And for cosine function, we do not need to copy this into the phasor. It's a little long. But guys, please bear that in mind. We have such a relationship for the conversion only for cosine function. If you have sine function or other type of functions, you have to convert them to the cosine functions first, and then convert cosine to phasor. But so far, this has already been the cosine function, so I don't need to do anything. Okay? Omega t. First of all, we don't need to worry about t because t is not included in the phasor form. And omega is not important for the phasor at this moment. Leave it alone. The next important thing you need to include in the phasor will be the phase angle, negative 30 degrees. So in other words, after you convert one cosine function from time domain to the phasor form in the fixed domain, you just need two factors, one amplitude, two phase angle. Between these two numbers in the phasor form, normally we use a small symbol, looks like an angle, to separate these two things. The term before this blue angle is the amplitude, but in the phasor we call that as the magnitude. Okay, the 400 by square root 2 here is the magnitude. The number after this small symbol is denoting the phase angle of this AC term, whatever. Okay, so in other words, by reading the phasor form given here, we know this is a vector in the frequency domain. Its magnitude is 400 by square root 2, and its phase angle is negative 30 degrees. Yes, please.
The solution just have a 400.
Yeah, I see. Yes, yes. You may notice the notation I used here is different from the notation used in the solution. Give me just 1 minute, okay? So after you finish this conversion in the fixed domain, as I mentioned, this phasor form has already been vector, and we are able to plot this vector out in the complex plan. So the complex plan consists of two axes. In other words, this should be a two-dimensional space. The horizontal axis is our real axis, and the vertical one is the imaginary axis. And that, in other words, any vector, any point in this two-dimensional space should be a complex number. Okay, we talk about the complex number later, okay? And if I want to plot this phasor current I in this two-dimensional space, I just need to determine two things. So what is the direction of it, and what is the size of it? Its direction is given by this angle, so negative 30 degrees. In this plotting, we always use the positive direction of the real axis as reference. By doing that, the negative 30 degrees is an angle given here. This is about negative 30 degrees compared with the real axis positive direction. And along this direction, the size of the magnitude will be 400 by square root 2. So in other words, I will draw a vector given here. This is our I vector, and the size of it is 400 by square root 2. Normally, this is procedure to convert the time domain cosine function to the fixed domain phasor form. But you may have already noticed my answer is different from the one given in the solution. If we go back to the question, Okay, here you can find angle is fine, but the magnitude for this given answer in the solution is just 400 with negative 30 degrees. The reason here is the one given in the solution is actually the average current, but what I'm plotting here is the instantaneous current. What's the difference between them? You may go back to our cosine function here. So have a look at this sketch here. I have mentioned that 400 by square root of 2 in the cosine function is the maximum current that this AC current can reach. But actually, we are not able to keep this 400 by square root of 2 in all the time for this cosine current. At some moment after the peak current value here, at some other places, the current value is much lower than 400 by square root of 2. This is the feature of the AC currents, AC voltage, and AC power, okay? So if we want to evaluate something like the power or voltage or current for the AC circuit, it's unfair to always use the maximum value. In such case, we are going to use the root mean square value, or in other words, the average value. But in my notation, in my work shown here, after I finish the transformation from the time domain to the fixed domain, did you notice my notation? I just write a capital I. This capital I, that means the root mean square value. But in the solution, for the part A, above the letter I, can you see a vertical bar? The horizontal bar? That bar is indicating this result is the average or root mean square current. So in the cosine or sine functions, if we are able to know the amplitude of the cosine function or sine function, how to calculate the root mean square value? Okay, you can do the integration and divide by the period t to calculate that, but the result should be very simple. The root mean square value of the cosine or sine function should be the amplitude divided by square root of 2. This will be important. So in this unit, you are going to do this process many times. Okay? So for the part A, we have already known the maximum amplitude is 400 by square root of 2 for this cosine function. Correspondingly, the root mean square value is, of course, 400 by square root of 2, then divided by square root of 2. The two square root 2's are cancelled. The result is 400. This 400 is the root mean square, or average value of this AC current. And normally in this unit, because we are going to face the power evaluation, the energy calculation, so we are going to focus on the average value only in most of cases. So in the test, assignment, and final exam, we normally do not need to write down this, because this is indicating the phasor for the maximum value of the AC current. Normally we don't need it. We will write what is the average current instead. So in other words, for the part A of the question, the phasor form of the AC current should be I. So everyone, I hope you can just follow the notation. So give a bar above it to indicate you understand this is the average current, okay? And if you write down this thing in your work, I can also understand what you are going to tell me, okay? So this thing is equal to the root mean square value of the amplitude of the AC current. So actually I gave the notation is I RMS. This is the magnitude of the new vector, and followed by the angle of this AC current. Okay, this is the meaning of this notation. Of course, for this question, result is 400 square root of 2. Amplitude divided by and try again. What's wrong? Divided by square root of 2. So this is used to convert the amplitude to root mean square value, okay? And the angle, negative 30 degrees. So result is just 400 with negative 30 degrees. Just that. By the way, unit remains same, amps for current. So is this okay, everyone? Yeah. Of course, this question is not asking us to plot this vector in the complete plan, but for our further analysis, we try to draw it out. Okay. So now I will just plot this vector in the complete plan. So should be very easy. Real axis, and this is the imaginary axis. The negative 30 is about here. This negative 30 below the real axis. Okay, and its size we assume. Just highlight this average one, and its size is 400. Okay. In other words, in this case, we got a new vector. Even though this vector is pointing to the same direction as the previous one, but the meanings are different. Okay, and the magnitude is changed as well. Okay, based on this vector in the complete plan, we are going to derive the other form of this vector, which is called rectangular form. So actually, at the beginning, I have mentioned, so all the points or vector in the complete plan are actually complete number. This complete number consists of real component and the imaginary component. The real component of the vector is actually, let me use in blue pen, okay, is the projection of this vector on the real axis. So this is the real components. I'm using IE to denote the real component of this I average. And the projection of the vector on the vertical axis gave us the imaginary component of this vector. The rectangular form of this AC current, I write at the bottom here, right? Because they are also in the complete plan, so I can use the same notation. It's actually a complex number. It's the real component of this vector plus J by the imaginary component of this vector. This J is the indicator of the imaginary component of this complex number, so it should be simple one. Okay, calculation should be pretty simple for this given question, because within this triangle we have known the angle is 30 degrees, and the size of the vector I is given, which is 400. Based on 430 degrees, we should be able to evaluate the real component and the imaginary components easily. So the real component, get out, my fault. The real component should be the magnitude of this vector multiple cosine negative 30 degrees. Yes, I'm labeling the 30 degrees only, but because this 30 degrees is below the real axis, so the angle is actually negative 30 degrees. Okay, this gives us a real component, and then plus the imaginary component, which is the magnitude of this vector multiple sine negative 30 degrees. So this gives us 400, that's magnitude, multiple for cosine negative 30 degrees is square root of 3 over 2. Then plus J multiple 400 by, for sine negative 30 degrees give you negative half. Answer is 200 by square root of 3 plus, should be minus, okay, minus J 200 amps. Okay, I don't have my calculator in my hands, so I'm not going to calculate 200 by square root of 3, but that should be quite the answer for this case. Everything okay? Everyone? Yeah. Okay, so before moving on to the next part, I just want to emphasize again. So first of all, if you want to convert a time domain function to the frequency domain to the phasor form, you must recognize the cosine function. If you have the other types of functions like sine or whatever, so that function must be converted to cosine first, so before moving on to the phasor. Okay, this is the first point. Second point, in this unit, when you convert one cosine function to the phasor, so the amplitude of the cosine function must divide by square root of 2 to convert that to the actual value to be the magnitude of the phasor. But the angle, the phase angle, can be copied to phasor directly. And the third point, There are two different forms to represent a vector in the complete plan in the fixed domain. First one is the phasor form. The phasor form must be like the format magnitude followed by the angle. And the other form is the rectangular format. It must be like real component plus or minus j multiple the imaginary component of it. So these two ways to represent a vector in the complete plan are equivalent between each other. So it depends on which question asks you to do what, okay? But if no requirement is given in the question, normally if you want to calculate multiplication or division, so the first phasor form will be much easier. But if you want to add up two things or subtract some things in the complete plan, so the rectangular form will be very convenient. Okay, this is what we are going to do in the question 1A. So any questions? Oh, good? Yeah. Now let's move on to the question 1B. So I don't want to do it because you have understood how we produce the phasor form, the rectangular form, and part B is very similar to the part A, so I skip it. But before that, please notice in part B, the instantaneous current IT is in the sine function in time domain. So as mentioned, this sine function must be converted to cosine function. So in the solution of part B, you can see the IT is changed from sine function to the cosine function. This is the first step, okay? But how to convert sine function to cosine function? Sine whatever is equal to cosine, so whatever minus 90 degrees. Very simple. You must have known that. I just want to remind you here. Got that, okay? Part C is similar. So I leave that to you guys to figure this out by yourself. In part C, the tricky thing is the IT in time domain is the summation of the two cosine functions. One is cosine, one is sine, the summation of these two. Of course, if you like, you can use the trigonometric formulas to finish this calculation in time domain, but I don't suggest you to do so because that calculation is pretty long and complicated and redundant. The best way to calculate this summation is to convert each of these two factors into the corresponding vector in the complete plan and finish your calculation of the vectors in the fixed domain. After that, convert back or whatever. That's much easier. Okay? So the solution has shown you everything. So please just go through this part by yourself. Should be pretty simple.
So we have a test, and we have to add two complex numbers together.
It may happen. Of course, you have to show that. If we have such question in the test, so that means we want to say if you understood how to do that or not. So you have to show me all steps. So as mentioned, for example, if you are talking about the part C, you can do either way. So add them together in time domain and convert that to the phasor or rectangular, whatever. But as I mentioned, and also as suggested by the solution, so we are converting each of the two terms into the fixed domain and add up these two vectors in the complete plan to finish the calculation. So in the test, you have to show me which way you are doing and your calculations and final answers. Depends on the questions. You mean for example, question 3? I mean the 1C, right? No, you can't. I roughly understand your question. So are you asking me, can I just leave my answer like this here?
No, from there to the final 7.0.
For this one? What? Oh, this is very last step, right? If the question didn't specify what format we want, then either this one or this one would be good. Because we mentioned they are all equivalent between each other in the complete plan, so all good. But if the question is asking you, please give me the phasor form of the current, then you have to give me this one. If I ask you to give me what is a rectangular form of this current, then you must give me this one. So it depends on questions. All good? Yeah. Okay, this is question number 1, and let's move on to the question number 2. Question? Oh, good. Did I answer the question? Yeah. Okay, for the question number 2. Now, for the single phase circuit shown in the figure below, the current I, so that means this current I is 10 magnitude followed with 0 degrees angle. So this is actually a phasor form, okay? Amps. The part should be RMS. Should be RMS. So actually, most of notations like this you see in this unit are RMS. Sorry for the confusion of the notations, but in the future, if we didn't state otherwise, they are all root mean square values. Okay. And we compute the please compute the phasor I1, I2, and the voltage V. Okay, voltage V is the voltage across the voltage source. I1, I2 are the sub currents going through these two sub branches. This is the whole story. So let's have a look at the solution. Actually, this is a very simple circuit analysis. You can use whatever way you want to finish your calculation, like the KCL, KVL, mesh analysis, up to you. But for this question, because the two loads, two branches are connected in parallel between each other, and that capital I current is the input current to that parallel block. So for this question, the easiest way is to use current division to determine I1 and I2. Okay, because I1, I2 are just two sub currents sharing the total incoming current. Okay, so current division should be the easiest way. So let's move up and change the pen. So question number 2. So quickly, what is current division? So some of you may have already forgotten that, right? So if you got two branches are connected in parallel between each other, R1, R2. So I'm using resistor as example, okay? And for this parallel connected block, the total incoming current is I. So same notation as the one given in the question. And for these two separate branches, we got I1, we got the I2. And by using the current division, you can use one single formula to determine the I1 or I2 quickly. So I1 is a fraction, so part of the total current, because I1 is a sharing part from this capital I, right? At the bottom should be R1 plus R2, the total resistance or total impedance for the parallel connected block. And on top, if you want to determine the current going through R1, you should put R2 on top. Verse-wise. Okay, if you want to write down I2, I2 is the same thing, R1 plus R2 by capital I. But on top, this time, you put R1. Okay, this is the current division rule used in the parallel block system analysis. I'm using DC circuit as an example. In the AC circuit, this rule remains to be true. Okay, so for this question, actually, the solution is using the current division to determine the I1. So because I1 is current going through the middle branch, so for calculating the I1, actually what we are doing is, I'm using blue one anyway, I1 equal to the fraction by the I. At the bottom, it should be Z1 plus Z2. Now we are in the AC circuit. We are in the impedance of these two branches, okay? And on top, because I'm going to calculate the I1, so Z2 will be on top. So this is just formula used for this question. And then next step is to put the known values into this formula. The capital I, as given by the condition of the question, is 10 with 0 degrees. And for the two branches, the Z2 is pretty simple. It's just negative J6 ohms. So we put negative J6 here. And at the bottom of the fraction, is negative J6 as well. The Z1 is 8 plus J6. So just that. This is how we use the current division. And for the calculation, that should be pretty easy, right? But if you want, I can go through that for you. First of all, at the bottom of fraction, positive J6 and negative J6 can be just cancelled between each other for this question. And the whole thing is changed to negative J multiple 6 over 8 multiple 10 with 0 degrees. For this part, this is one rectangular form because you can see the J, you can see the imaginary component, right? And the second half is a phasor form. For such calculation, normally the best way is to make them to be in the same format. I prefer to use the phasor because the phasor is very convenient for the multiplication. So I want to convert the first term to phasor from rectangular. This negative j 6/8 is actually 0 plus j by 6/8. Oh, sorry, my fault. Negative 0 plus j multiple negative 6/8. For this small term here, in the complete plan, it indicates a 0 real component and a negative 6/8 imaginary component. This vector is actually at here. Can you see that? Oh, good. For such vector, its angle must be negative 90 degrees. But in the future, you can just speed up by recognizing this in here. If you see a negative j, this negative j is always negative 90 degrees. So this can be speeded up. Oh, my fault. It's not negative anymore because I want to put negative sign into the angle. So this is changed to 6/8 with negative 90 degrees. Just that. So by using one single step, we are converting the first term into the phasor. And this phasor will be used in our calculation here. So 6/8 with negative 90 degrees. And then multiple the next term, this whole thing. So when you calculate the product between two phasors, so the result will be a new phasor representation. The magnitude of this new phasor will be the product of the two magnitudes. So 6/8 multiple 10. The angle will be added together, which is negative 90 degrees plus 0 degrees. So result is 60/8. Again, I don't have calculator. I leave that like this one with negative 90 degrees. And again, if the question is asking you to leave the result in the format of the rectangular, this negative 90 degrees is corresponding to a negative j. So this gives you negative 60/8 j. Same thing. Then finish. Okay? Okay, this is a very quick calculation. And for the I1, so I1 is done. I think this is right, so I've done that. For the I2, if you want, you can do the same thing. But for this question, if you are using the current division again for calculating the I2, you may have a small trouble. Because if you want to use current division, the I2 will be equal to, at the bottom should be 8 plus J6, then minus J6, multiple 10 with 0 degrees, right? On the top, this time, we have to put Z1 on top, but Z1 is pretty complicated, which is 8 plus J6. If you do so, you are facing a problem. You have to calculate the ratio between two complex numbers. Normally, this will be hard for you. It will take a longer time, maybe 5 minutes. If you have calculator, maybe 3 minutes. But if you can do that, maybe can speed up your calculation. But the best way to increase your speed is to use KCL. Much easier. So this is KCL. See here, at this node, current I is going in, and then split into two subcurrents, I1 and I2. So far, out of these three currents, we have already known the total current I. We know the I1 from the first part calculation, so only the I2 is unknown. So I2, sorry, my fault, I should not use this lowercase. So I2 is equal to the total incoming current minus the portion of the I1 to finish. And for this current I here, we have already known is 10 with 0 degrees. For the I1, actually, I have done the calculation. I said I1 is, where is that? Is how much? 60/8 negative j. I1 is negative 60/8 j. This is known. So 10 with 0 degrees is actually 10 plus j 0. No, not 0 degrees. I mean j0 is just the 0 imaginary component. Okay, and then plus 60 over 8j. So result should be much easier. So you got 10 plus 60 over 8j here. So much easier. Okay. Okay, this is about the two step currents in the 2 branches. Voltage, very simple. So voltage is the I2 multiple the Z2. But actually, if you enjoy to do the calculation of the complete numbers, you can use I1 by Z1, the same thing, because all 3 branches are connected in parallel. The total voltage provided by this voltage source is the same as the voltage shared by each of the 2 branches. So Ohm's law should be sufficient. Good, guys? Might skip that? Good? Okay, so this is question number 2. Okay, part B is asking us to draw the phasor diagram showing the I, I1, I2, and the voltage V respectively. Because we have already derived all these answers, and just using the magnitude plus the angle to draw these vectors in the complete plan, then finish. I want to skip it. Good? Can you handle that by yourself? Yeah. Okay, the time for now is 9:40. We have 5 more minutes. I don't think we have enough time to go through the long questions. So anyway, let's have a quick look on the part A of question number 3, and then we finish, okay? In this question number 3, we got a voltage source. So Vt equals to 4 by cosine omega t plus 60 degrees. This voltage source is connected to an impedance, the Z. The impedance of Z is 2 with 30 degrees ohms. In other words, the layout of this circuit is really simple. AC voltage current, voltage source connect to a load, the Z. I think this is the V, right? This V here. This is everything. And the question A is asking us, given the operating frequency to be 60 Hertz, so please determine the expression for the current and the instantaneous power delivered by the source as a function of time. And I think that the current should be pretty simple. Using one single Ohm's law, or if you want, you can use the KVL. Okay, that matter for this simple question. Okay, so we are able to determine the current in the circuit. So actually, in the solution, we are using Ohm's law. Current equals voltage divided by the impedance. But here, the voltage has already been in the phasor form. So in other words, this calculation is carried out in the fixed domain, not in time domain. Okay, and don't forget, you must convert the amplitude in time domain to the root mean square or average value in the magnitude for the phasor. Okay, angle just 60, easy stuff, divided by impedance. So impedance is just copied from here to here, and based on these 2 numbers, so we find the ratio of them to be the average current in this question. Easy. Oh, good? Yeah. And I think the question is asking us to calculate the current delivered by source. Sorry, here, one more thing. We need to determine the current in terms of time. So after you determine this current in the fixed domain, one more step to convert this average current phasor form back to time domain. So in time domain, okay, the frequency will not change. If you have such frequency for the voltage, the frequency for the current remains the same. So this part is just copy. And when you convert something from the phasor form back to the time domain, so the function must be cosine all time. So cosine is no problem, remains the same. Angle, okay, we got 30 degrees as the angle of this average current phasor form. So this angle will be copied here. So all this stuff are pretty easy. But when you process the amplitude, be careful. Now we are converting the average magnitude of the phasor back to time domain. You have to multiply the average magnitude by square root 2 again to reach the maximum amplitude. So square root 2 from the root mean square value, multiple another square root 2, give you 2. So this is why we have 2 here. Okay? Okay, this is how we derive the time domain thing for the current. For the power, okay, in time domain, the power, the real power, is equal to the voltage by the current. then we derive such answer. You may ask me, can I use the formula we studied in the week 2 to calculate this power? For example, this week we studied the complete power, my fault again. The complete power equal to V by I conjugate. And the real power in this case, if you want to do the calculation by using the knowledge we learned in this week, okay? The real power is V magnitude by I magnitude by cosine theta. Can this work? You may try it out by yourself. But after you finish this calculation, you will get a single number rather than this function. The reason is, so guys, bear that in mind, important, okay? So if you are using such formula to do calculation, this P is actually the average voltage rather than the instantaneous power. Is that right? So this P is the average power, not the instantaneous power. So I highly suggest you to do a calculation by using this formula, because in the future you are going to use this one. So after you finish this calculation, you will get a single value. The value should be equal to 3.46. Is that reasonable? It's totally reasonable. So please double check the instantaneous power here. The final answer for this instantaneous power is 3.46 plus 4 by cosine 2 omega t plus 90 degrees. The second half of this equation, so 4 by cosine 2 omega t plus 90 degrees, is oscillating, but its average is 0 for this cosine function. So after you finish the evaluation of the average power by using this time domain instantaneous power, the result is just 3.46 to be the average power. That result should be same as the one we derived by using this formula. Okay? So in other words, by using the formula we learned in the second week, we can evaluate average power only. And also, I want to remind you one thing. So when you try to use this formula to solve the question, what's the theta? Actually, in the lecture yesterday, I have already explained the theta. This theta should be the theta, the angle in the power triangle. This theta is equal to the angle of the voltage minus the angle of the current in this question here. For this particular question, what is the angle of the voltage? The angle of voltage is 60. So what is the angle of the current? That should be 30, right? So 60 minus 30, which is 30. So in other words, if you want to use this formula to do calculation, this theta should be 60 minus 30. All right, thank you very much. And because I have another class, we have to finish here. For the remaining questions, please try them at home and refer to the solutions. If you have any questions regarding the tutorial problem today, please send me an email, or we can discuss face to face. Thank you, everyone, for attending this class. Okay, online students, we have done our practical class now, and because I have another class, so I have to terminate this Zoom meeting. If you have any questions, please feel free to let me know. Thank you very much. Thanks. So, everything okay? Next week, yes. Yeah. So the questions we can't finish today will be your homework, and you can just try them out and ask me the question if you have troubles or not. Okay? Of course. Just sit here, it's fine. If somebody asks you to go out, then go out. But I don't know. Okay, everyone, is class okay? Is it, sorry, is that too slow? Okay, maybe I can speed up because some online students, they didn't study the energy unit before. They don't understand the phaser thing at all. And last week we have the so-called iPad problem in the lecture. They emailed us saying they don't understand the phaser thing at all. They don't understand that phaser diagram showing in the slides. So we are slowing down. But I think slowly we can speed up once these guys catch up. Okay. Hi. Oh, good. Thanks. Because I have to write something, so hope to see you on Microsoft Teams. Okay.